Welcome to The Explainer. Today, we're tackling a massive question. One that sits right at that crossroads of biology and technology. And we're basing all this on a really fascinating paper called The Requirements and Possibilities of Creating Conscious Systems.
All right, let's just jump right in. We are surrounded by smart tech, right? But there's this enormous difference between a machine that can, say, calculate or navigate and one that's actually aware. So the real question is, can we actually bridge that gap? Is it possible to engineer a mind?
So before we even dream of building something conscious, we've got to get on the same page. We have to define our terms. Because let's be honest, when we talk about consciousness, we're usually mushing together a few very different ideas.
And this right here, this slide really gets to the heart of all that confusion. Think about it. On one side, you've got a supercomputer. It's unbelievably intelligent, right? It can do calculations we can't even wrap our heads around. But it has zero autonomy. It just sits there, waiting for the next command. Then on the other side, you've got an earthworm. Totally autonomous, it's out there navigating its world all on its own. But you wouldn't exactly call it intelligent. The paper argues that consciousness is something else entirely. A third, totally separate category.
Now, if you're going to take an engineering approach, this definition is absolutely crucial. We have to forget all the magic, forget the idea of some mysterious soul. The way it's framed here is that consciousness is a physical process. Simple as that. It's just what the brain does. It's a product of its biological hardware. And that's the key, right? Because if it's a physical process, that means, in theory, we can reverse engineer it.
Okay, so let's break that down a little. First up is subjectivity. That's the idea that your experience of the color red is yours and yours alone. Nobody else can feel it for you. Then there's unity. Think about it. The sound of traffic, what you see on the street, the feeling of the wind, it all just melts together into one single unified now. And finally, you've got intentionality. This just means your thoughts and experiences have meaning. They are about something. For a machine to be truly conscious, it would have to take all three of these boxes.
So, if we're serious about building a conscious machine, we really only have one working model to study, right? The human brain. To even begin to grasp the engineering challenge ahead of us, we first have to understand the specs of our own biological hardware, our wetware.
And this is not a new question by any stretch. For thousands of years, we've been wrestling with this. We went from thinking of consciousness as some kind of mystical soul to something totally separate from the body. And then finally, we get to folks like the psychologist William James, who basically said, hey, this is a function of a physical organ, the brain's cortex. And it's that shift in thinking that makes an engineering approach even possible in the first place.
All right, so let's really treat the brain like an engineering project for a minute. What are its specs? Its technical specifications. How does this thing actually stack up against our best and brightest technology?
The scale here is, well, it's almost impossible to wrap your head around. The human brain has something like 100 billion neurons. Just try to picture each one of those as a tiny little computer, a single processor. Now, imagine 100 billion of them, all connected together in this network of just staggering complexity.
And memory? What about memory? Well, the source material estimates that just the cortex, and that's only one part of the brain, has a storage capacity of around 300 terabytes, and they get that number from its 300 trillion synaptic connections. Just incredible.
And this is where you can really see where all that human complexity comes from. Look at this. A rat, 15 million cortical neurons. A cat, 300 million. A chimp, our closest relative, has over 6 billion. But then you look at the human brain, and it makes this absolutely mind-boggling leap to 11.5 billion. That jump, that's a massive, massive increase in raw processing power.
So how does our best tech stack up against that? Well, this chart compares the brain's memory to the IBM Roadrunner, which was a top-of-the-line supercomputer when this paper came out. You can see the brain clocks in at 300 terabytes, while the computer's at 98. So in terms of just raw storage, we're actually getting into the same ballpark. It's getting close.
But this slide right here is the real kicker. This is the challenge. The brain runs on just 20 watts of power. That's less than a dim light bulb, and it fits neatly inside your skull. That supercomputer, on the other hand, it needs 3.9 million watts, and it takes up 1,000 cubic meters of space. The brain isn't just a little more efficient, it is orders of magnitude more efficient. And that is the engineering miracle we somehow have to replicate.
Okay, so we know the scale of the problem is just immense. So, how do we actually start building? What's the game plan?
Well, the authors suggest we stop thinking about it as some unsolvable mystery and start thinking about it like a systems engineering problem.
And this quote here from the AI pioneer Marvin Minsky, it just perfectly captures the mindset you need to have. The brain isn't magic, it's a machine. Yeah, it's an incredibly complex one for sure, but it's a machine all the same, and it follows the laws of physics just like everything else.
So how do we build insanely complex machines? The paper brings up a great example, the Boeing 777. Think about it. It's got millions of parts, millions of lines of code. There's no single person on Earth who understands that entire aircraft, top to bottom. But by using systems engineering, we can design it, build it, and manage all that complexity successfully. The argument here is that the brain, it's a similar kind of challenge.
So here is the proposed blueprint. The key is you don't try to program consciousness directly into a machine. That's not how it works. Instead, you build what they call a hybrid architecture. So you're combining different kinds of AI, like symbolic reasoning and neural networks. Then, and this is critical, you give it a massive stream of sensory input from the real world, just like our own eyes and ears give us. After that, you let it learn, like a human baby does, through pure experience and interaction. And the really profound idea here is that consciousness isn't some feature you install. It's a property that just emerges once a system with the right foundation gets complex enough.
And really, that's the whole idea in a nutshell. The path to artificial consciousness isn't about cracking some clever self-awareness algorithm. It's all about the architecture. It's about building a system with the right foundation, plugging it into the real world through senses, giving it the power to learn on its own, and then just creating the right conditions for consciousness to just arise.
Which leaves us with a pretty fascinating final thought, doesn't it? If consciousness really is an emergent property of complex, interconnected learning systems, well, what other systems out there are on the verge of waking up? Could it be the internet, the global financial markets, or maybe something we haven't even imagined yet? Engineering consciousness might not be the end goal, it might just be the beginning.